Can you all hear me?
Yeah, Kai, I can hear you. Can you hear me?
Yes, I can hear you perfectly.
Okay, thank you.
All right, Kai and Arnab, you guys can go ahead and mute and turn your video off, and then after Mia intros, we'll kick it to you.
Okay.
All right, thank you.
Hi, everyone. Welcome. My name is Mia. I'm one of the producers of TWiML Fest, and we're super excited to have you here. This session is the AI for Industrial Application session hosted by Arnab Biswas, a data scientist working at Carrier Global Corporation, and Kai Lichtenberg, CTO and data scientist at Charrington. Before we get started, I'd like to thank our sponsors for their support of this event and TWiML Fest. I also want to make sure everyone notes that the chat is at the bottom and you can send questions there at any point. We'll be monitoring the chat, and I believe there will be some time for Q&A. So that's all I got. I'd like to turn it over to your hosts. Have a great session, guys.
Yes. So hello, everyone. Arnab's on there. Yes.
Hello. Yeah.
Hey. So maybe we'll start with introducing ourselves a little bit more in detail, maybe. Arnab, if you want to start.
Yeah. So my name is Arnab Biswas. I work as a data scientist in the eco-energy business of Carrier Global Corporation. I started my career 15 years back as a software developer, and over time I have worked in companies like Cisco Systems, Nokia Siemens Networks, mostly building server-side applications. Right now, I work in machine learning, and my area of interest area of work is basically predictive maintenance for HVAC assets, the topic on which I'm going to talk today. Yeah, that's pretty much it.
All right. So first of all, Arnab, thanks a lot that you're on, because it's very late in India now. It's I think it's 10:30 p.m. right?
Yeah. But that's not a problem, Kai.
Okay. Yeah. So it's 10:30 in India. It's 8 p.m. No, 7 p.m. here in Europe, and I think it's morning in the US, right? Okay. So yeah, my name is Kai. By training, I'm actually a mechanical engineer. But I'm now working quite some years on data analytics / data science, AI use cases in the industrial settings. And I've worked for Bosch, a very big automotive supplier, for some years, where I worked on some also predictive maintenance topics and predictive quality. And after that, I started a company with a few others working on industrial radiology, which is actually very similar to medical imaging. We'll see that in my presentation. And as of November 1st, I will be head of industrial solutions at CodeCentric, which is a IT consulting company here in Germany. Yes, and so we wanted to start off, before we start with our presentations, to talk a little bit about how working with AI is probably a little bit different in industrial settings than in IT-based areas, I'd say. And so in my experience, when you work on such topics in the IT industry, it's everything is much more open and collaborative in this area. You'll find basically dozens of open source projects and code examples for all kinds of topics. And in my experience, at least for the data science projects I've seen so far throughout the years, that's very different in industrial settings. And it's much more secretive and more on your own than in other areas. And yeah, Arnab, I was wondering if, I mean, you've probably seen both worlds, right?
Yeah, actually, I have seen both the world, and I completely, like, I have spent probably more than a decade in IT organizations, and what I have seen there is, like, as you said, right, I appreciate their openness. The way the open source softwares are, like, so open source software is a de facto standard here, there, and why should I reinvent the wheel when I can use open source softwares?
Yeah. Yes. I always compare this. So for the last few years, I've been working a lot on industrial radiology, and as I said, it's quite similar to medical imaging. But in the medical area, you will find plenty of papers, data, code, examples, and courses and stuff. You will find almost nothing in the industrial area, and this also, although this area, this industrial radiology area, is pretty large too. It's not that it's a very small thing, and therefore you can't find anything. But also, one interesting example is I've seen a paper from Stanford actually, but not from their vision group, but from their civil engineering department. And this paper really had a fundamental machine learning craftsmanship flaws, I'd say. And I mean, although Stanford has kind of one of the best vision groups in the world, there's apparently no networking from the classical engineering guys to those guys, because they would have immediately spotted this. I don't want to kind of say which paper it is, because I don't want to blame those people, but it kind of resembles how this in this area people are doing their work, very different from people in the IT area. And actually, one more fun thing, in my corporate time, I was asked by someone, he was not from the IT area, he didn't know that, but he really asked me if for a problem we can avoid using one of the big frameworks from Google or Facebook and do it on our own. And that kind of shows how, yeah, I mean, that's ridiculous. Everybody working in this area knows that it's ridiculous to try to build PyTorch or TensorFlow on your own in order to use that. And yeah, so there's a lot of work to do. And in my opinion, I mean, it's due to the way of general working in this areas. It's very important for the companies working in these areas to keep trade secrets and stuff like this. And in my feeling, I mean, it changes, but until now, engineers in this field do not really understand that it's very beneficial if you have more of this kind of horizontal networking and cooperation, and that this can be a very big advantage, right? So
Correct.
Yeah. So I mean, we are like 22 people in the Zoom call. So maybe if anyone has something to add to this, some experiences or stuff, you can quickly unmute yourself and say something about your experience. Otherwise, we'll start with our presentations.
So another thing which I have observed is in the traditional industry, right, compared to IT, in the traditional industry, um, the traditional industry is very slow when it comes to the adaptation of latest technologies and innovation. I remember maybe a few months back, I was attending a course by Singapore University, and it was about data science for building. And like they have lessons where they are saying, they are explaining why Python is better than Excel. So I see the same thing in the traditional industry. People are still stuck with the old set of tools, and probably there is they are not ready to pick up new tools. And that's one thing. Like, they need to be open, they need to communicate with each other, share ideas, and probably then adapt technologies.
Yeah, I mean, you have to remember that in this kind of industries, the innovation cycles are much longer than in the IT industry. So they are much more used to kind of make small steps and make their products better with small steps. So for example, think of internal combustion engines, for example. I mean, this is a process that's going on for like more than 100 years to make those things better and better and better. And what we now see with Tesla, for example, they're having a very different way of innovating, and that's causing problems for the traditional automotive suppliers and automobile manufacturers. And yeah, this kind of working also has impact on how those companies adapt technologies like AI, for example.
Completely agree.
Yeah. All right. So, Arnab, you want to start with your presentation on
sure.
predictive maintenance?
Correct. I can go ahead. Let me
Awesome.
share. Screen. Yeah. Yes. Can you see the presentation?
Yes.
Okay. So I'm going to talk about predictive maintenance, how machine learning is used for predictive maintenance of HVAC assets. Now, HVAC stands for heating, ventilation, and air conditioning. These are the equipment or assets which are used to control the temperature, humidity, and air quality inside the buildings. The buildings could be residential houses, or it could be commercial buildings like a hotel, or or an office space, or a hospital, or a shopping mall. So what you see here in this slide are two types of HVAC. This is called a chiller, and this is called a rooftop unit, or RTU. And this is a setup or the arrangement which we generally are familiar with. This is an arrangement which is used to pump, say, cold or warm air inside the office space. But the actual heating or cooling of the air happens generally in a centralized place by HVAC assets like this chiller or RTU. Now, HVAC accounts for 40% of the energy usage in commercial buildings. So 40% is a big number, and that's where it's very important that we design, install, and maintain the HVAC assets properly. However, in today's presentation, we are going to focus only on the maintenance portion of it. Now, like any other asset, like any other equipment, HVAC is also made of multiple parts, and over time, for various reasons, the part fails. Once a part fails, the HVAC equipment that may stop working completely or partially, and that's when the user literally feels the discomfort and heat. That's the reason maintenance becomes important. Traditionally, there are two types of maintenance. One is reactive maintenance and one is proactive maintenance. In reactive maintenance, what we do is we wait for the failure. Once the failure happens, then only we service the equipment. But in proactive maintenance, or which is popularly known as annual maintenance, an equipment gets serviced at regular intervals. There could be failure, there may not be failures, but the equipment gets serviced, and if necessary, parts get replaced, etc. Now, predictive maintenance comes somewhere in between this reactive and the proactive maintenance. And in predictive maintenance, what we try to do is we try to predict the health of an equipment based on its previous health or historical behavior. Say a predictive maintenance system predicts that there could be a possible failure on a particular day or within a particular time range. In that case, what we do is just before the failure, we go for a service of the equipment. We do the servicing just in time. Now, here is a formal definition of predictive maintenance. It's about predicting equipment's failure over a time period based on its historical behavior. There are three goals of predictive maintenance. One, predict a failure, predict whether an equipment is going to fail in the future. Number two, predict days to failure. And number three is what could be the possible root cause of failure. Now, these days to failure and the possible root cause of failure, right? Those are important because based on those, we can plan the service of the equipment. Now, let's take a look of the PdM architecture in the era of big data and IoT. You can imagine that this is a commercial building and there are various equipments, including the HVAC. There are other types of equipments as well, including HVAC, and all these equipments are attached with some kind of sensors. The sensors are continuously pumping data into centralized controller, and from that controller, the data travels all the way to database or data lake. Once we have historical data about an equipment, the data is fed to a predictive maintenance system, and the system tries to predict whether there could be a possible failure or not. So if the system predicts a failure, generally, not always, generally it goes to a human in the loop. The person, who usually a domain expert, looks into the data and tries to validate whether the prediction is proper or not. If the validation goes through, then a ticket gets raised and the ticket gets dispatched to probably a service person. Now, once the service person receives a ticket, he or she may try to fix it remotely if possible, or if not, he or she may have to travel all the way to the building, replace the part, or do whatever is needed. Now, it's not that predictive maintenance is something new. Predictive maintenance is there. Predictive maintenance is being solved even before the machine learning era. Earlier, we used to use rule-based algorithms, model-based strategies to handle predictive maintenance. Now, with the advent of big data, more computation power, we are trying to use machine learning for that. Now, like any other machine learning problem, the first step is to understand the business problem. And once we understand the business problem, we need to convert it into a machine learning problem. We can handle a machine learning predictive maintenance. We can convert predictive maintenance in a machine learning problem by several ways. If we handle it as a binary classification, then the problem statement becomes something like this. Predict if an asset is going to fail within next 2 weeks. I'm just using 2 weeks as an example. So the problem statement is like this. Predict if an asset is going to fail within next 2 weeks, and there could be two possible outcomes. Yes, it's going to fail within next 2 weeks, which is probably 1, and no, it's not going to fail in next 2 weeks, which is probably 0. Now, if we handle it as a regression problem, then we need to predict the amount of time left before the next failure, which becomes the remaining useful life. We can handle it as a multi-class classification. In that case, the problem statement becomes like something like this. Predict if an asset is going to fail in next 3 weeks, or it's going to fail in next 2 weeks, or in next 1 week, or it's not going to fail in near future. So we have 4 states here. The last way which I'd like to mention, that's probably the most popular way, because here we are combining both. We are combining the time to failure and the reason for failure. So here the problem statement is something like this. Predict if an asset is going to fail within next 2 weeks for a compressor issue. The time to fail remains constant, but the reason for failure, that changes. So it could be like tell me if an asset is going to fail in next week for a compressor issue, for a heater issue, for an electrical issue. So all these issues, root causes creates one different class. Now, whether we should go take the track of regression or classification, I'll say that depends on the business. Now, if the business allows, we should probably go for regression instead of classification. We can imagine that regression is nothing but classification with infinite number of classes, and hence it's always easier to solve a classification problem than a regression problem. In a different context, we can have a single stage model or we can have a multi-stage model. Say we have a multi-stage model. For example, what we can do is in stage 1, we try to predict the number of assets which are going to fail in next 2 weeks. And in stage 2, we try to identify the root causes for failure for all those assets from stage 1. Next comes data collection. So I am going to mention about a particular documentation from Google, which is called Rules of Machine Learning. And that rules of machine learning, they say that if you want to launch an application with machine learning, the first step is to launch the application without machine learning, because that's the phase when you start collecting the data. The same is true for predictive maintenance. Possibilities are that in your organization, people are already collecting the data which is relevant for the predictive maintenance. This is where the domain experts, they will start helping. They know the data, they know which data is relevant for solving this particular type of problem. Now, as you can see here in predictive maintenance, these are generally the raw data points which are useful, and but they broadly comes under 2 categories. One is the time series data, or the data which has a time component, temporal data, and one which doesn't have time as a component, which is the static data. Now, within temporal data, we have again few broad categories. One is health, how healthy the equipment is, whether the equipment is able to maintain the temperature or humidity while consuming optimal amount of energy or not, right? Then comes weather, raw data points related to outside weather. Then comes maintenance. Maintenance is of particular interest because maintenance is something using which we create the labels as well as we create features. So under maintenance, we generally track the failure history, repair history, the root cause of failures, the part replaced, and other stuff. Then there could be other type of time series data which is completely out of which are not related to the asset, which could be, say, for example, building occupancy. On the other side, for static data, we have equipment metadata like model, make, model, and manufacturer of the equipment, metadata of the building, the climate zone, and the geographical location of the building, and all the stuff. Now, once we have all the data from various sources, what we are supposed to do is we have to consolidate them. We have to consolidate them into a tabular format so that these particular data structure can be fed to an algorithm. Now, the structure actually depends on the algorithm to which we are going to feed. Here I am taking a particular example of binary classification, and probably the data can be fed to a gradient boosting machine kind of algorithm. So what is shown here, that each row represents the state of an asset on a particular day. So here on 13th January for a particular asset, these are the metadata of the asset, these are the health information about the asset, these are the maintenance data related to the asset, and this is the label, or whether the asset was, based on the maintenance data, whether the asset was healthy or unhealthy on that particular day. Here 0 means healthy, whereas 1 means unhealthy. Now, next is we should do some amount of pre-processing where we have to handle missing values. So one thing is, like when it comes to IoT devices, right, they are notorious when it comes to missing values. Like there could be lots of missing values just because the sensors were not working. If the sensor was working, controller was not working. If the controller was working, there was a outage in the data pipeline. So missing value handling becomes a critical piece of of the machine learning pipeline. There are standard ways like forward filling, backward filling, there are interpolation, but then domain specific specific ways of filling missing value is also very helpful. This is where the domain experts can help. Say, for example, I want to fill missing value of vibration on 1 p.m. Tuesday. Now I can fill it with last Tuesday 1 p.m.'s value or Tuesday 1 p.m.'s value averaged over last 1 month. Whatever be the strategy, it needs to be validated with cross-validation. Then comes outlier handling. Even now for predictive maintenance, we should keep one thing in mind: outliers are our friends. We should actually build new features using outliers, but whereas the traditional or naive approach is just to drop the outliers. So please, please, please don't drop the outliers. If there are duplicates in the data, or outliers in the maintenance data, duplicates in the maintenance data, it could possibly indicate there are some human errors. Again, consult with the corresponding team, consult with the domain experts. Now, here comes the most interesting piece, I'll say, which is feature engineering. So it is like this. The data gets collected from the sensors, say at a very high frequency. Say the temperature of an asset that gets collected from the sensor every 15 minutes. But on the other side, I'm supposed to predict whether an asset is going to fail or not in every 1 hour. Now there is a frequency mismatch, and hence I need to do aggregation. There is another reason for which we need to do aggregation. Like what happens is generally the data collected, the health or weather data collected by the sensors, they are, because of their higher frequency, they are very noisy. Now, for example, say if I take the daily average of the temperature of an asset, probably I'll find out that the asset's temperature is rising slowly rising just before the failure. Now, if I consider 15 minutes interval of data, I can't see that signal. That signal would be hidden in the noise. So again, I need aggregation for that as well. Now, I know I need to do aggregation, but what would be the window size? Here, the thumb rule is how far in future the model has to predict. That influences how far in the past the model has to look back. So say I want to predict if an equipment is going to fail in next 7 days, then I should probably aggregate the data for historical data for last 7 days, last 14 days, last 21 days, or something like that. If I want to predict 1 month in advance, probably I should consider 1 month, 2 months, 3 months as the lag window. So again, window size needs to be validated using cross-validation. Now the point is, okay, we need aggregation. I know there is a strategy for a lag window, but what are the different statistical mechanisms which I should use to do the aggregation? Here, since we are doing machine learning, which is at times which is like brute force, right? So here we should try building features with as many variations as possible, right? As Jeremy Howard says, like, should you try blah, you should try blah blah. So you should try all the different statistical functions, and then based on feature selection mechanism, you should select. But what I have seen is generally the count of our outliers within a particular interval of time, or say the number of peaks within a particular interval of time, all the stuff works great. Again, this is where you should talk to the domain experts. They have huge amount of insight about the kind of features which works well. Even from the data using date, we can create a lot of features, and these kind of features introduce a sense of time to the algorithm. Using static data, we can build features, and then comes maintenance data. My experience is that with say health information or weather information, if we build a model, the performance goes to a particular level. Then once we introduce the features built with maintenance data, the performance goes to a new level, like it goes to a next level. So what kind of features can we build? Say the days since last failure could be a good feature. Days since last failure because of a compressor issue could be a good feature. So if my compressor has failed just 1 month down, 1 month before, the probability of its failure in next 7 days is very less. Similarly, we can have other features like days since last maintenance, etc. Now, irrespective of the fact whether we do regression or classification, whichever route we take, by the time it's kind of clear that we have kind of time series data here, right? If we take the classification route, probably it's a time series classification problem. Irrespective of that, since we have time series data, when we do cross validation, we have to maintain the timely manner between the training data and the validation data. Training data should come from the past, whereas validation data should come from the future. Now, another thing is, if I have training data and test data, how should I split? I can split them based on the time, as we are doing for validation data, but we can split them based on the equipment ID as well. So the number of equipments is, we build the model with a set of equipments and we test the model with another set of equipment. This is particularly useful when in production we can expect new equipments. Next come metrics. What are the metrics which we should use? Again, I'll say this depends on the choice of our like whether we are taking a classification, multi-class classification, or a regression. But we need to think about we should keep two things in mind, that this is a typical imbalanced data set problem, right? Here, the number of days over which an equipment is healthy is much higher than the number of days on which the equipment is unhealthy. And then I should also be mindful about the high cost of false positive. Say, for example, if my model predicts an equipment is going to fail, and a service person visits the equipment just to find out that everything is working all right. And I'm sure my boss, my organization will have to be at my organization has to be at the cost, and my boss is not going to like it. Now, what kind of algorithms are useful? Again, I'm going to go back to Google's rules of machine learning, and they say that choice of algorithm really depends on the phase of the machine learning pipeline. So if your machine learning pipeline is in the phase 1, we should always build simpler models and simpler features, because the goal of phase 1 is to make sure that the data is reaching to the feature store or the feature engineering code, and the features are getting built, they are fed to the model is doing what it is supposed to do. Once we are able to do that, then we start building complex features. And with that, we should get some amount of enhancement in the model's performance, good amount of enhancement in the model performance. And once we reach the plateau for that, that's when we should get into the phase 3, where we start picking up complex model like complex deep learning models or complex ensembles and all the stuff. Here, this is a table which is again recommended by Google. Google Cloud has a documentation on predictive maintenance. I have those things in the reference section, so I don't want to comment about the particular choice of algorithms. But again, if you or your organization is in the phase 1 or phase 2 of machine learning model building, probably you can just start with gradient boosting machines, like with tabular data with time series, gradient boosting machine works just fine. And then slowly, as the pipeline matures, again, move to other algorithms of your choice. Next comes the model serving. So here the question is, do I need to do a real-time scoring? Like as and when the data flows from the IoT devices, should I do a prediction? The answer is probably no. The business would be happy enough if I probably do the scoring once in a day or once in a particular interval, once I have enough amount of data. So batch scoring should be sufficient, and that's actually easier compared to the real-time scoring. Now, once the model is deployed in the production, that's when the monitoring starts. That's when the actual work of the data scientists start. So I have built the model, I have deployed it, and that's when I should start evaluating the performance of the model with respect to the ground truth, which is coming from the future. So say my model has predicted that an equipment is going to fail in next 15 days. I should track that, whether the equipment is really failing, if a ticket has been raised, whether the service person has found that the equipment is about to fail or not. Now, say the model works well in the production, but then slowly I start observing that there is a slow degradation in model's performance. There could be various reasons. I am highlighting just 2 points here. there is a possibility that there is a bug in the data pipeline. So I as a data scientist, probably I just maintain the machine learning pipeline, whereas there is a huge data pipeline, right? And say there is a new category which has been introduced, my model is not aware about that, and the model is not able to handle that. Or there could be drift in the data. For example, I have built model, which is more likely the scenario. Say I have built a model with the summer months data, and now winter is approaching. So my model is not, my model doesn't know the distribution of the data changes, and my model doesn't know how to handle it. So I need to go for retraining at regular intervals, so that as the new data comes in, a model starts picking things up. So that's kind of about it, how predictive maintenance can be done using machine learning, how it is done for the HVAC industry. Here are a few reference documents. If you want to explore further, please look into those. And the slide deck would be available here on this link. With that, I'm open for questions.
Yeah, Arnab, thanks a lot. Very hands-on, very, very good. If you really want to start a project in this area, then you can. There were really some good tips that you can use if you want to start. Also, I really didn't know that there's so much energy used for HVAC in buildings. That's crazy. It's 40% of all the energy. That's a lot.
Yeah, that's really a lot.
Yeah. So, does anyone have a question for Arnab? Feel free to just unmute yourself. Let me have a look at the chat.
Yeah. Yeah, sure. I'll post the slide deck link here in the same chat. Maybe once the question answer session is over, I'll put it.
So Alan is asking, what do you think is the best for your application? Is supervised, unsupervised, or reinforcement learning?
Well, it's of course supervised. There are, again, I'll say it depends on the maturity of the organization. So if it is not Google or Facebook, probably we should start with supervised learning. And specifically, as I was talking, right, that if an organization has health data, weather data, and maintenance data, like when the equipment was actually working and when it was not working, that information, then we do have features and labels. So supervised learning, we should think about. Now, the problem with reinforcement learning is, for reinforcement learning, we need to do a lot of tests, right? Now, nobody is going to allow me to do the test with their HVAC assets. So that's going to cause discomfort. That's going to cause discomfort for the users or for the consumers in a shopping mall or in a hospital. So
yeah,
at least for predictive maintenance, reinforcement learning is not probably a good way. But for energy efficiency applications, I see reinforcement learning is becoming a popular way.
Yeah. So what I've also seen in predictive maintenance is that it's anomaly detection. Well, it's basically, it is supervised learning, but it's about if you have a signal, then you kind of train a model to not to predict, to find something in the signal, but to reproduce the signal. So, for example, if you have a temperature sensor, then you can use other data from the unit. For example, yeah, I mean, I've done this for a gearbox. So you need the torque and the revolution speed, and then you can, and some other data like the temperature outside of the vehicle and stuff. And then you can create a model that predicts the temperature. And then you teach in this model with the state of the unit when it's good, when it's working. And then you kind of have a virtual sensor that is predicting the temperature. And when your true sensor on the device finds that the temperature is differentiating from the predicted signal, then you have something, then there's something happening that should not happen. And so you can find anomalies, for example, in signals. That's also something I've seen in predictive maintenance. But I mean, technically it's supervised learning because you train the model with a supervised setting, but you kind of try to find anomalies with this setting.
Yeah, makes sense.
Yeah. Then have you seen any ticketing tools that do the prediction for you already? I know ServiceNow, a product used in my previous company, starting to use AI modules for prediction. So I think the question is, do you know any
no,
off-the-shelf products? Okay, no, me too. I don't know anything. Yeah. And do you have any opinion or information related to the chemical industry?
No, I'm not sure if the question is again related to predictive maintenance of chemical industry, but I'm not really familiar. But generally, the whatever I spoke about, right? Although this presentation was focused towards HVAC, maybe apart from the raw data points, the other things will also be applicable for chemical industry. The way you define a problem or the way you do feature engineering, all the stuff should match.
Okay, so and what brought you to work with predictive maintenance, and why do you have the interest in predictive maintenance?
See, okay, something which Kai was mentioning, right? That the traditional industry, it's huge, and the kind of impact which can be created by using AI in traditional industry is also huge. So if we see this is little different perspective, it's from economics, and if we see that the GDP in US and in Europe, that's slowly decreasing, and there is something called TFP, which is about creating more outputs or value out of the same resources. That is also decreasing, okay, over time. Now, where the economists are wondering is, okay, Silicon Valley is saying, okay, we are going through continuous innovation. We have AI, we have ML, we have robotics, but they are not getting reflected in the economic growth, right? Yeah. So I think there is a big gap between the traditional industry and the capabilities, AI capabilities which we have, which yes. We need people who sit in between and do that stuff.
Yeah, I totally agree with that. So I think you have to work much harder on adaptation of these technologies in the industrial area, but also there's a lot more potential to kind of really do important stuff and have big impact, because there is very few at the moment, very few people. Yes. Working on this stuff in this area, so you can be the trailblazer here, but you need to work hard on the adaptation and work on stubborn people and tell them that AI is a good thing.
Right.
All right. So maybe I'll start with my part.
Yeah, sure. I'll stop
sharing.
Yeah.
All right. I can share my screen. Continue. All right, do you see the slides?
Yes.
Oh, awesome. All right, so my topic is predicting quality with AI. And the first topic I want to show you is about reducing waste in production. So I've chosen an example from the automotive sector that I personally have worked on before. And it's about the production of this crankshaft here. Crankshafts are probably one of the most complicated and also expensive parts in an internal combustion engine. A lot of surfaces here of this part have to be manufactured with a very high precision, those shiny surfaces you can see here. And also these surfaces are not on a common axis on this part. So usually you have those surfaces on a common axis. It's not the case here. And from a production point of view, that's a nightmare. If you have that, it's very, very complicated to do it good. And the production I've seen here had up to 20% scrap on this part, which means that up to 20% of the raw parts that go into the production did not make it into an engine because they did not meet the accuracy requirements. And that's really a lot. That's also, for this kind of part, it's really expensive to have it like that. All right, so what's happening during the production of this part? Basically, a raw part arrives at the production line, which does not have any of those beautiful machine surfaces here, but it really just has roughly the shape of this part. And those surfaces are then gradually brought onto the shaft in various milling and turning processes, and then the surfaces have to be hardened. Yeah, they really have to be very hard. And then the last step is accurately grinding those surfaces so they are very, very, very precise. And they have to be precise, they have to be hard, and they have to be smooth in order to that they can rotate in the engine without any problems. And so I'll not explain what this part does in the engine, but if you don't know what this part does, then just think of it as a turning part in the internal combustion engine, which is very, very complicated to manufacture. So it is possible to record a great deal of data over all these different and individual steps of production. This can be, for example, temperatures during individual work steps, or forces that occur during milling and turning, certain parameters during the hardening of this shaft. So this can result in hundreds or thousands of different features that you can record during the production of this part. And also, at the end of the entire production process, there are measurements taken that ensure that the part is okay and meets the required dimensions. And this is basically the criterion to sort out parts with flaws. So if the dimensions are not correct, they are sorted out. So that's the label. Now, we have a high dimensional data set for each component and a result to whether the part is okay or not. And of course, that smells like machine learning, right? So we should use machine learning to predict that. And what I personally find very exciting about this type of problem is that you have an extremely wide range of possibilities for feature engineering. It is always about some physical process being measured, and there are many ways to use knowledge about this process for feature engineering. For example, you could, if a certain operating condition, for example, of a machine, of the milling machine is influencing the surface of the shaft, then you can use this information to create new and additional features to your data set. And there are a lot of these things you can do with this kind of data. But you have to really think about what exactly you want to achieve with this kind of application. Because one thing is clear, as soon as all the data from the shaft is available, it is already produced, yeah, it's already there, which means you cannot save any money, right? I mean, you cannot save money if it's already there, and you couldn't prevent any flawed dimensions, for example. And I mean, maybe you could save a little bit of time because you don't have to measure the part at the end, but of course this is not a big advantage. And so in this particular case, the aim was to just save the last step, the grinding of those shiny surfaces here. And because this is the most expensive and longest process in the production. And it was a great saving when you can predict before the grinding happens whether the part will be okay or not, so that you can sort it out and don't have to do this very, very expensive process. And in this particular application, a lot of data was already collected during the production process, which is by no means standard in the industry, in the industrial settings. In most cases, there's no way to get the important data, either because they don't exist or they are only used to control the machine. If you want to do such a project, you very often have to start by installing sensors or taping into the bus systems of the communication systems of the machine. And then you have to have set up an industrial IoT architecture to collect the data, and then a whole data management to collect the data. And once you have that, then you can start collecting data so that you can train a model at some point. And that can be very large projects. In the case of this crankshaft, the possible savings were very large, so they were happy to invest here. And that's something that you should always think about when you maybe choose your first project you want to do for, let's say, optimizing your production, try to find something with a high impact, and then tackle it. Or maybe something where you can have low-hanging fruits where you already collect data, then maybe you can use this, but try to have as big of an impact as you can think of. Yeah, and one last thing to mention here, it's not that the engineers are not working on those production processes. I mean, they are doing something to improve the quality of their processes, of course, but they're almost exclusively nowadays even working with classical stats and few features, or by working out very fancy physical models to really understand what's going on. And machine learning really shines when you have very complex links between things that can cause a problem. And that's actually in this kind of production very often the case, especially for yeah, very complex components, of course. All right, so next, let's talk a little bit about the modeling. As I said, you can pretty fast end up with a very, very big data set in this kinds of applications, because you can measure and feature engineer a lot of data points in production processes. The biggest one I've seen was actually on Kaggle for a competition hosted by Bosch, where I worked at that time. And they anonymized the data because they didn't want to tell which part this data was about, so which component. That's again kind of a secretive. That is how this industry works. And but let me say, it was about a complex machine part, not that different from this crankshaft I've showed you. And they also had a lot of different configurations for this part. So they ended up with thousands of features and millions of rows, which led to a table with billions of entries. So a very big data set. And also the data was a real life data set, of course. So it was very messy as hell. And we had all kinds of different data types and possibilities to convert to categories or numerical. For modeling, there really was only one competitive type of model, that was gradient boosted trees at that time. That is actually something I've learned working on those kinds of use cases. You have like 80% of the time to work on the data and find good features, then 15% on finding ways to tackle class imbalance. That's something Arnab already also talked about, because that's, of course, you always have to deal with imbalanced data here, because you want to try to find very, very rare things mostly. And then 5%, I would say 5% for the model itself. And I've seen actually two things here. When you have small data and want an easy to understand model, you can use decision trees, really just ordinary decision trees, so that you can kind of understand what's happening in the decision. And if you want a performance model, so a model that focuses on performance, then you very often end up with gradient boosted trees, because you can feed them basically arbitrarily messy data and they work. And I mean, that was actually a few years ago. So nowadays, I'd say I would also try deep learning, of course, for that kind of problems. But yeah, I mean, gradient boosting is really it's still a very, very performant model for those kinds of problems, tabular data. All right. So then the next thing I want to show you is a topic from radiology. However, not from the medical area, but from the industrial area. And most of you will probably only know this from the medical area, but in industrial applications, X-rays are very common too. It's actually pretty much about the same things as for radiologists. You have to find things on X-ray images that do not belong there. And on the picture here, for example, those are X-ray images of weld seams. And this is, for example, what holds pipelines together. And when you look at the edge of this weld here, for example, you see some pores in the image that are air inclusions here. And those do not belong there. They can cause that this weld seam breaks, and you don't want to have that. And also, like in the medical area, it's often done by, or it's mostly done by humans. So this kind of repetitive work is, as in medical imaging, not very good for humans, because you have to look at pictures again and again, hundreds of times often. And yeah, so automating via AI, pretty much the same like medical imaging, is a good idea here too. Also, the type of techniques you use is very similar to medical imaging. Use segmentation, object detection, classification to find flaws in the parts. And those flaws are just like in medical imaging, often very small and very rare. And yeah, so the only difference is, and that's what I told at the beginning, it's very hard to find data, because virtually no one is open sourcing any meaningful data here in this area. There are some very small data sets, but they are really just for showing purposes like this here. And you have to collect those data and prepare it on your own. And yeah, that's very different to the medical area. So I've picked one more use case also from the industrial radiology area. This is very interesting. It's about image enhancement, actually. There's a lot of effort especially in the automotive industry, to use computer tomography in the production process. And they do that because there's a very big difference between manufacturing of internal combustion engines and electrical cars. The combustion engine is made of a lot of different parts, and those parts are produced independently from each other. And they can be assessed for quality independently, often even not in the at different companies. And that's very different from components in electrical cars. They are produced as compact and very dense units, and often very highly automated. And you have very few chances to look into those components during manufacturing. And that's why computer tomography is interesting here. But the thing is that computer tomography is often very slow to make images for a significant amount of parts during the production. And AI can help here. When you do faster imaging with a CT machine, then you get worse pictures. They are with a higher, lower signal to noise ratio. And a CT image consists of many individual pictures, as you maybe know, which are then assembled to a three-dimensional representation of the part, and or of the component. And any slight noise in this individual images add up to a bad overall 3D representation of the part, and you have problems finding flaws, for example, in this 3D representation. So have a look at the picture on this slide here. That is a test specimen for CT imaging. It's not an actual part from a car, but it's a test specimen. And the left image has problematic noise in it, which you really can't see, right? I mean, it's so subtle and hidden in the 16-bit depths of the image that you can't even see it unless you use some kind of different coloring, which is this here. It kind of looks fancy, a little bit rainbow coloring, but it's a repetitive scale to first of all see all of the 16-bit depths in this build, and then you can see that there is a very, very subtle amount of noise in this picture here that is not in this picture. And this picture takes much longer to take on the CT machine than this one. Now, with image-to-image models, like for example, the dynamic UNet, which is provided by FastAI, you can easily create a model that gets rid of this noise. Basically better than any classic approach, because those kinds of models, as you probably know, can take all those kind of spatial things in those pictures into account that normal classical noise reducing methods could not do. And that's interesting, because this can actually be a tipping point where you can, for the first time, make those tomography images with enough speed and quality to actually use them in mass production settings. And yeah, I mean, what I want to show you with this is that it's not always about like directly predicting some data points, but that, for example, directly predicting the quality, like I showed in the first example. AI is can also be used to make all kinds of technical processes better. And I mean, this here, what you see on those slides that's really a very specific use case, but it stands for a lot of other use cases where you have this kind of disruptive potential, where AI can be the tipping point to have this improvement that you usually do not have in those kinds of industries, because the progress here is normally very stepwise and slow. Yeah, so to kind of find these use cases and know what to do, that's what I've learned often a very creative process, to think of ideas and analogies to improve technical processes, use your knowledge of similar AI topic you've seen. I mean, this image enhancement stuff, that is something I've seen in the fast AI courses. And when I saw this tomography thing, I immediately realized, okay, you could use this kind of model instead of generative adversarial networks, which are sometimes really hard to train, and kind of build a model that for each part you show it. So when you have a new part that you are producing, then you can train it into this kind of noise reduction model, and then you can reduce the noise for your production setting later on. And to my understanding, it's really important that engineers in this area really get out of their bubble and dive into this AI community, which is, of course, working in a very different way, but it's very important for them to do that, because only then you can see those kinds of things and work on your specific topics. Yeah. All right. So few slides, a lot of talk.
Very interesting, Kai. So, but Kai, how the industrial radiology, right? How popular is this among the traditional industry, like all the big players?
Oh, there is a lot of industrial radiology everywhere. So, I mean, there are two kinds of different ways to do it. It's you can do it on site. So when you, for example, build a pipeline, then you have some people out there who are have mobile X-ray machines, and then they take pictures of the weld seams, for example, of a pipeline. So each and every weld seam of a pipeline has to be X-rayed or maybe ultrasonically evaluated, but X-rays are very common here. And I mean, think about those segments are, I don't know, 15 to 20 meters long, and think about how many weld seams you have on a 2,000 kilometer pipeline. And so there are made a lot of pictures. And then in the other setting, you do this really in the production. And that's often for parts that are very critical when it comes to security. For example, in the aerospace industry, there's a lot of radiology, because you really want to make sure that your parts are good. And also in the automotive area, it's at the moment not used for like every part that is produced, but they check kind of the batches that they're doing, for example, electrical motors, to really find if there's something going wrong and a whole batch is malfunctioning, because you really can't see it with your own eyes when these components are assembled together in the end.
Okay. And how popular is the use of AI for industrial radiology?
Oh, absolutely not popular. I would say that industrial radiology is like 5 years behind medical imaging, at least. And or maybe 10. I would say 5 to 10 years, but it's really not common to do it with AI.
Okay.
Okay, maybe let's check the chat.
Yeah, so there is a question: for imaging models as discussed using flaw detection and quality validation, typically how much data would you say is the minimum required for an effective model? Would you leverage an existing highly trained model with transfer learning and fine tuning so that you need significantly less data?
Absolutely. There is no way you wouldn't start with transfer learning. And there is also no way you wouldn't start with kind of ImageNet pre-trained models. Absolutely. There's no doubt about that this will give you an advantage. You don't need to train on pre-train on similar data, because the ImageNet pre-trained models really have a lot of, it's the best starting point for any vision task I've seen so far. And also, you very often have the pictures you have in one application are very similar very often. So you have often very, very reproducible settings when you take these pictures, and they are very similar. So it's often the case that you don't need that much data to train a model. Also, pre-training with other X-ray images can help, because there are specific features to X-ray images that can where it helps that you pre-train with other X-ray images. Good augmentation, of course. You can think of augmentation that applies to X-ray images, like you do in medicine. And yeah, so it's always the question, how much data do you need for? So that's actually something that most of the customers ask also, how much data do I need? You can't really tell, of course, because you have to try it and then you know how much data you need. But for use cases where you really have very similar pictures and where the setting is very reproducible, you can often achieve good results with like 100 pictures. Also, of course, it really depends on what type of model you're using. If you're doing segmentation, classification, or object detection, and how often the thing you want to detect is really on the pictures. And yeah. All right. Are there any more questions?
Yeah, I see another question with regard to crankshaft example. If we wish to detect defect much before finishing stage, say at turning or milling stage, what would you like to have? More elaborate data set or more fine tuning of the model?
I would say more data. So one funny thing, I think it was not the crankshaft part, but a use case, but a pretty similar use case where we found out that the ambient temperature had a big impact on the. I think it also was a milling process of a part, because when the ambient temperature changes, the part also shrinks or grows, and that's something that you would not find if you don't track the ambient temperature. And maybe somebody would say, if you collect data for predictive quality, then probably someone who's not into data science would ask, why do you need the ambient temperature? And so I think that really the more data you can have, the more, at least it won't hurt to have more data. But of course, I mean, there are restrictions to that. You can't kind of buy 1 million sensors and apply them to the machine. It has to be. There are restrictions, of course, but I would say that the most important thing is that you have someone who knows data science and someone who exactly knows the process and what's happening there. Someone who really knows this production process, and those two together, maybe in one person or two persons, they should talk about which data you should have to create this model. That's actually something that Jeremy Howard is always saying, that he wants to see more people from those domains, like production engineers who take his course and use this to leverage it in their domain. And that's actually, that's absolutely true.
Yeah, so in the data science perspective, at times, like maybe a domain expert can't think that this data can contribute to solve this particular problem, but they actually, for example, in my predictive maintenance case, probably a domain expert will say, okay, all the temperature and weather related data is sufficient, but the moment we have, say, the footfall data, occupancy data, right, that gives a completely different perspective.
Yeah.
Like it helps the model to see something which it can't see.
Yeah, absolutely. I've seen that multiple times, that you that there are things you didn't think that really have an impact that had an impact. I know, for example, one case, it was not that the data was not included, but they realized that if they opened the gate of their production facility, then there was cold air coming in, and that influenced the production process. I mean, who would think of using the signal from the door, if it's open or closed, putting it into a data set for predictive quality? But it would have worked. I mean, you would have seen that.
Correct. Interesting.
Yeah. All right. So
I don't see any other question.
No. So Arnab and I, we are always around on Slack. So if you have any questions, just write in the TWiML Fest channel or write directly. Yeah.
Just
Thanks
wanted
a
to
lot.
add, great presentation, guys. Awesome.
Thanks, Sam.
Sam, a special thank, like I would like to thank you specially for building this community. I have used your machine learning engineering ebooks. They are like super helpful. I recommend it to everybody.
That's awesome. Thank you.
Thank you.
Thank you so much, everyone. Thank you, Kai and Arnav. It was a really great session. And thank you, everyone, for attending. This video of the session will be available on the session page that you used to join. So feel free to reference that. And thank you so much, everyone. Have a great one.
Thank you. Bye.
Bye.